So in this portion of lecture one, we're going to be talking about real gas behavior as opposed to ideal gas behavior. So for real gases, for the most part, gases under standard conditions behave ideally. So if we think about all of the gases that we know of, oxygen, nitrogen, helium, whatever. Under standard conditions, they behave as an ideal gas, and this is because they have a lot of thermal energy. They're moving around very quickly. They don't interact very well because they have so much thermal energy. Now, as soon as we start going under very high pressures, molecular volume starts to become an issue because those molecules start to squeeze together. And if they're squeezing together, they have to make room for each other. Remember, ideal gases said that molecules and atoms have no volume, but we know that they must have volume because they're matter, and so they take up space. Now, it turns out we can adjust the ideal gas law to account for the volume of atoms or molecules for a particular gas. And so we'll have two different correction factors, A and B. The first one we're going to look at is B. And B is a species-dependent correction constant to account for molecular volume. And we can look at the correction to volume as equal to nRT over P. So that would be our normal expression in the ideal gas law for the value of V for volume. But we're going to add NB, so the number of moles times the correction constant B. Obviously, the number of moles affects how much volume the molecules take up, because the more you have, the more volume they're going to take up. Now, if we look at molar volume under standard conditions for different gases, we can see that for the most part, they stick very close to 22.4 that we would expect under 1 atmosphere, not 1 bar, but 1 atmosphere. And so 22.41 for an ideal gas. So Cl2, very big molecule actually. So it's probably got the biggest impact here at 22.06. CO2 is 22.3, NH3 is fairly ideal at 22.4, etc. You can look at the rest of those. Now, if we start looking at higher pressures, so we'll use argon as an example here. Let me just grab my pen. So down here, we look at argon and we see around 200 to 400 atmospheres of pressure. So that's roughly equal to 200 to 400 bar as well. Very high pressures, we start to see that the molar volume starts to differ from ideal. The molar volume is bigger than what you would expect for an ideal gas, which is why we have to take the ideal gas law and add that NB in there. The other factor that comes into play, and we always have to consider, are intermolecular forces. So generally, intermolecular forces between gases are very small because they're a gas, they're moving fairly quickly, they have a lot of thermal energy. So the forces between molecules doesn't really come into play. However, as you start to get to low temperatures or high pressures, they start to become fairly important. And so those intermolecular forces also get corrected with a species-dependent constant, A. And so here, under non-ideal behavior, we can see the effect of intermolecular forces, and we see that they are generally a subtractive force, and this is because they create, if we look at pressure instead of volume, so if we look at the pressure, because those intermolecular forces between molecules are making them stick together, they generate less pressure. Because they're not moving completely independently of each other, they stick together or move a little bit slower as doubles or triples or whatever, but they don't move independent. So pressure becomes lower than expected under fairly cold temperatures. Now, xenon is a very large gas. It's a large atom, and so we start seeing deviations even at fairly reasonable temperatures, even room temperature. Down here, we start to see a deviation or at 400 Kelvin or at 600 Kelvin. So the larger the species gets, the bigger factor that we have for that A factor. And so here's our equation here. If we look just at P, we have nRT over V. That, of course, is the regular expression for pressure and the ideal gas law. And then we provide our correction factor, which is minus A N over V squared. Remember, N over V, so that's number of moles over volume. So that's essentially molarity. So we're looking at A times the concentration squared. We can just put all of that on one side. So we say P plus A times N over V squared. So that's our pressure and the pressure correction factor equal to nRT over V. Now we can combine both of those last two equations. So we have something that corrects volume, we have something that corrects pressure. We can combine all of those into a single modified version of the ideal gas law, and we get something that looks like this. So we have our pressure correction factor, P plus A N over V squared. This is our correction for intermolecular forces, or an attraction correction, sometimes also called a pressure correction. And then we have V minus NB, which is our correction for particle size. And that, of course, is still equal to nRT. Now, if we take a look at some of these A and B values, we can see that they do vary by quite a bit depending on both the size of the molecule or atom and the intermolecular forces associated with that. The biggest variation tends to come in the A constant with those intermolecular forces, because you obviously have some molecules that are highly polar or are very large and have very large London forces. And so here, something like acetic acid, we see the A value is 17.7, whereas for something like helium, it's just 0.03. So that's a huge factor difference. Whereas the difference in B is 0.1 down to 0.02 for helium. So even though they have a very large difference in size, it's not quite as large as that impact from the polarity. Now, deviations from ideal can be seen in our next graph here, where n is 1 and we're just going to keep the T at a constant 500 Kelvin. And what we see is that you get both positive and negative deviations from the ideal gas law can occur, sometimes for the exact same compound under different conditions. So it just depends on what the conditions are. And so here we see some of our real gases. So if we look at something like helium, which is a very low attraction species, so that A value doesn't really do much. And so something like helium would be volume dominated. The volume has a much larger impact than something with just 2 electrons. And so we get nothing but positive deviation here. This line right here is the ideal gas, because we're looking at PV over RT. And so for an ideal gas with 1 mole, that would always be 1 under all situations. So here is something like helium or neon is always going up, or even argon, ideal gas, fairly small. Xenon, as we start getting bigger, you see xenon starts to have a negative here, and then rising up to a positive. Something like H2O, water, which has it's still a fairly small molecule, but has a very large dipole because of that hydrogen bonding, goes well into the negative regions. You can see it goes below the level of our graph here, way down. And so if you look at something like xenon, we'll go back to our xenon example here under high pressures, but not super high pressures. It's attraction dominated because of the London forces, but then as you squeeze it more and more and more, it is a fairly large molecule, and the volume begins to become a bigger issue here as well.